Get a fresh one. No. Right in between. Take the average of those two throws and you got it. Hey, Mr. French, your AP Stats teacher. It's time to do some Chapter 6 work, baby! Welcome back to Math Inc. Thanks for making it. Hope you enjoyed the previous videos. Thanks for watching. Hey, shout out to those folks that are completing their suggested practice. I have an update from College Board. This is the big update here. So we know that the test will be online. It'll be 45 minutes. It's also only going to be free response questions. I do not know yet if there's going to be an investigative task or a question 6. I'm going to wait until the beginning of April, so we should find out here in a little bit. That is what we know so far. There is no multiple choice on the AP exam this year, so you better be practicing your free response questions all the way up to Chapter 10, so through Chapter 10. So skip Chapter 11 and 12 through Chapter 10. Free response questions are what you should expect to see on the assessment. So we're going to talk about combining random variables today. I'm going to start with the computer. I have a little PowerPoint presentation. I know it might be kind of strange to read the computer screen, but that'll be fine. We'll get the hang of it. It'll be totally fine. We'll be good. We'll be good to go. All right. So many interesting statistics problems require us to examine 2 or more random variables. Let's investigate the result of adding and subtracting random variables. So we'll start with the addition. So we're going to say that let X be the number of passengers on a randomly selected trip with Pete's Jeep Tours, and Y is the number of passengers on a randomly selected trip with Aaron's Adventures. We are going to define T as X plus Y. So T will be defined as taking, let's assume that Pete's Jeep is going to merge with Aaron's Tours. So we're going to combine these 2 companies. What are the mean and the variance of T? What happens to the mean and the variance when we combine 2 distributions? So just a reminder, this is Pete's Jeep Tours. This is what we had in the last video. But here's Aaron's Adventures. So a few things to note. Aaron's Adventures looks like we do not have occupancy for 6. Aaron also has a highest probability of 3 passengers. We could calculate the expected value. Remember that we take each value, multiply it by its probability, and add it to the next one, multiplied it by its probability, plus the next one times its probability, so on and so forth. So if we were to do that with Pete's Jeeps, which we did in the last video, we have a mean of 3.75. So in the long run, the average number of people that are on his trips is 3.75. So after many, many, many trips, the average number of passengers for Pete's is 3.75. Standard deviation, so typically you're going to deviate by about 1.09 passengers, and that's Pete's Jeep's Tours right there. Aaron's is a little bit different. So if we were to take each value times its probability, add it to the next one times its probability, so on and so forth, the expected value for Aaron's Adventures is 3.1, and the typical deviation from that is 0.943. So on Aaron's Adventures, after many, 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 many adventures, the average number of passengers on those adventures is 3.1. And then here's our distribution here for Aaron's Adventures. So what's going to happen if we add them together? So let's think about this for a second. In the long run, we expect an average of 3.75 passengers for Pete's Jeep Tours. And then for Aaron's, we expect 3.1. So if we were to combine these companies, how many passengers should we expect? Well, 3.75 for this one, 3.1 for that one. Kind of makes sense that if we were to combine these companies, it'd be the addition of the 2. And that's actually true. So how many total passengers can Pete and Aaron expect on a randomly selected day? Well, Pete expects 3.75, Aaron expects 3.1. They will average a total of 6.85 passengers per trip. And we're going to generalize that to the following rule here. So if there's a variable, if we define a variable as T, being the addition of 2 random variables, then the expected value of T is really just the addition of the 2 separate expected values. So the mean of the sum of several random variables is the sum of their means. And that kind of makes sense. We'd expect, 3.75 for Pete, 3.1 for Aaron. So the total combination of those will be the addition of the 2. Now we're going to ask the question, how much variability is there in the total number of passengers who go on Pete's and Aaron's tour on a randomly selected day? So we're going to have to find the probability distribution of T. But before we do that, we have to do something huge. This is very, 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 very important. Independence is very, very important when you are combining random variables. We're going to be introduced to an idea that only works if you know that the two random variables or the multiple random variables that you are combining, you know that they are independent. Remember that independent means that the outcome of one event does not change the outcome of the next. They have nothing to do with each other. So if these were the Pete's, Jeep's, and Aaron's tours, we could assume that they're maybe like in different places in the world. So like Pete's, Jeep's tours could be in Africa, and Aaron's adventures could be in Asia or something like that. And so they'd be totally independent of each other. They're just combining their two companies into one. So you have to know, in order to combine them, in order for the next few rules to be okay, you have to know that the two events are independent. We're going to see why here in a second. Probability models often assume independence when the random variables describe an outcome that appears unrelated to each other. You should always ask whether the assumption of independence seems reasonable. I would like to go over an example where it would not seem reasonable. And in our investigation, it is reasonable to assume X and Y are independent since the siblings operate their tours in different parts of the country. Yep, big reveal here, big surprise. Pete and Aaron are siblings. Pete and Aaron are siblings. Whoa, big twist ending here. Oh man, Game of Thrones, watch out. We just found out that Pete and Aaron are siblings. Big reveals here on Math Thing. You may be asking yourself, holy smokes, this is a huge table here, Mr. French. What's going on? I'd like to break it down for you. I'm trying to, okay, cool. So I'm going to try, I got to be careful with my pointing. There we go. All right. So we're going to let t be x plus y. We're going to consider all the possible combinations of the value of x and y because we're combining these two companies. We want to look at how the distribution of the combination of the companies is distributed so we can start to look at the variance. One possibility is that Pete's Jeeps could get 2 passengers and Aaron's could get 2 passengers, which means that the combination of the two companies would be 4 passengers. Well, then what's the probability that you would get 4 passengers? Well, there's a 15% probability that you get 2 passengers from Pete and a 30% probability that you get 2 passengers from Aaron. Now, if you recall, independent probabilities, if you want one event to happen and another event to happen, you can multiply those probabilities. And since they're independent, the probabilities will not change. So if we know we have 2 passengers from Pete's Jeep, this is times the probability of Aaron's tours knowing that this happened, but remember that that doesn't change anything, so we can just multiply 15% for Pete, 30% for Aaron. So the probability that the total number is 4 is about 4.5%. Now another possibility, no, I guess, yeah, I do have a little arrow, don't I? Oh boy. Another possibility is that Pete's Jeeps could get 2 and Aaron's could get 3, which means that the combination is that there could be a day where we total have 5 passengers for the combination of these two tours. Well, this 5 came from a probability of 15% from Pete and 40% from Aaron. And so what we do is we times those probabilities together and we get 6%. Okay. We have to do this for every single possible combination. So you'll notice here, like Pete could have 5 and Aaron could have 2. There's a 20% probability for Pete having 5, 30% for 2, so the total is 7. Then you multiply those two probabilities and get 6%. So you do that for every single possible combination. And check this out. This is how it is distributed. Notice how technically we could have 11, but that's like the max for Pete and the max for Aaron. So that's very, very unlikely. 6 to 7 seems like the most reasonable. Remember that Pete's maximum, I think, was 4, and Aaron's maximum was 3. So it makes sense that 7 is the highest probability here. Notice how many times they're adding up to 7, 7, 7, 7, 7. So these are the totals. So this is the probability of the total number of passengers. And with their probabilities attached. Okay. So if we want to find the variance, remember we take the observation minus the expected value squared times each of their probabilities. Recall that the average of this is just going to be the average of the two added together. So we already knew that Pete should expect 3.75 and Aaron should expect 3.1. And so we know that the mean of this will be 3.85. We don't have to do anything with total possible combinations. Okay. So now we would use this number here, the expected value for the total, in our variance calculation. So 4. So that's this number right here. So 4 minus the expected value squared times its probability, which came from this, plus dot dot dot, yada yada yada, go all the way down to 11 minus the expected value for the total squared times its probability, and you add up all those and you get 2.0775. Holy smokes. Well, I'm just going to tell you that we knew a few things. We knew the variance for Pete's Jeeps was 1.1875, and Aaron's Tours tends to be 0.089. What do you notice about the variance of T? I'll give you 5 seconds. It's been 5 seconds. Notice anything nice? Anything convenient? Anything that might be helpful to not have to do this ever again? Ah, nice work. You got it. This variance is the sum of these two variances. Oh, that's so convenient. If we know the variance of each of the separate probability distributions, we can find the variance of what happens if we combine them together. As the preceding example illustrates, when we add two independent, huge, they must be independent random variables, their variances add. Heads up, standard deviations do not add. Do not add standard deviations, you can only add variances. AP Stats pro tip, this formula here is not given to you on your formula sheet. You do not have this for your formula sheet. So this is like the most common one that isn't given to you, but it looks very similar. It actually looks like the Pythagorean theorem. Turns out it does have some connections to the Pythagorean theorem that go way beyond the scope of this class. For any two independent random variables, if you are combining the two random variables, then the variance of that combination is the addition of the two independent random variables. You can add the two variances of the independent random variables, and that'll be the variance of the total. In general, the variance of the sum of several independent random variables is the sum of their variances. Few things. One, they must be independent in order for this to work. Two, you do not add standard deviations, you only add variances. So let's talk about finding differences. We aren't going to go over an example of this, so we'll just go over these ideas here. We can perform similar investigations to determine what happens when we define a random variable as the difference of two random variables. So let's say that we were subtracting two distributions or subtracting one distribution from another. We're going to take a look at one of those here in a second. So the means are pretty straightforward. If you are subtracting two random variables, then the distribution of the difference between two random variables is simply just the difference between those expected values. In general, the mean of the difference of several random variables is the difference of their means. Be mindful that the order of subtraction is very, very important. This is a bit of a giveaway here. It turns out this is a huge one. The variances will still add. The variance of the difference of two independent random variables is the sum of their variances. So this seems kind of weird that if you're taking the difference between two random variables, then you would subtract the expected values with the order important, but the variances would still add. I'll just tell you this. The more variables that you have mean more variability, whether you are adding or subtracting. The more variability you are introducing, so if you have a lot of variables, regardless if you're adding or subtracting, the only thing that you're doing is introducing more variability. You're only making things more complicated, and what that's going to do is increase your variance. Hello, welcome back. We're going to do some examples on combining random variables. The first thing is that we are going to talk about coffee. I love coffee. This is coffee. This is really nice coffee. Mug of the day. We have, this mug is from Gila Cliff Dwellings National Monument, New Mexico, established 1907. Okay. That taken care of. Oh, before we begin, any sum or difference of independent normal random variables is also normally distributed. If you're adding normal distributions together, you're going to get a normal distribution. Mr. French likes between 8.5 and 9 grams of sugar in his coffee. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08 grams. If Mr. French selects 4 packets at random, what is the probability his coffee will taste right? We're going to let X be the amount of sugar in a randomly selected packet. Then I'm going to define T as x1 plus x2. Remember, these are capital X's. That's important. So what do you think T represents? Right, T represents the 4 packets. I'm going to put 4 packets into my coffee. So let's think about a few things. My goal is to find the probability that the total amount of sugar is between 9 and 8.5. That is what I'm looking for. What's the probability I get a total amount of sugar between 9 and 8.5? If I was trying to find the mean of the total, if I expect 2.17 grams of this, 2.17 grams of this, 2.17, 2.17, it means that I'm just going to look, or I should expect the sum of all of these. So in total, I should expect, with these 4 packet distributions, I should expect 8.68 grams of sugar in 4 packets. But now I need to have the standard deviation. Eventually, I'm going to be doing a normal calculation. Remember that all 4 of these are normally distributed. When I add them together, I'll get another normal distribution. And so that's going to be very helpful with this probability calculation. So I'd like to find the standard deviation of the total. But remember, you can never add standard deviations. Now, it was given to us that the standard deviation of each packet so it'll typically differ by about 0.08 grams, but we cannot just add. So I'll show you something that you cannot do. This is bad. Never do this. What I'm doing right now, don't do it. This isn't good. Don't do it. Don't do this. This is bad. This is wrong. What can we add? We can never add standard deviations. We can add variances. Remember, the variance is just the squared standard deviation. Now, when can we add variances? So 2 things. Never add standard deviations. Second one, if you are adding variances, that means that you must know that we have independent random variables. This case here, I feel like it's fairly safe to assume we were randomly selecting these packets. The distribution in one packet should not be affecting the distribution in another packet. Once again, I'd like to go over an example where that's not the case in a little bit. So the variance is the sum of the variances, and the variance is the squared standard deviation. So we get a variance for this total of 0.0256, which means that the standard deviation, after we square root, is 0.16 grams. So we are trying to find the probability that it's between 8.5 and 9. I'll just kind of write that one more time here. Probability of 8.5 and 9. This is a continuous random variable, just a reminder. So that's what we're going to do. I'm going to draw my curve. I know that it's normal because the sum is from 4 normal distributions. And I'll do this. We have a mean of 8.68. We'll go a few standard deviations out and above and below. There we go. We are looking for the area between 9, which is exactly right here, 9, and 8.5-ish. Well, there's 8.52, so it's a little bit before that. We're trying to find this area here. So if I hit anywhere in here, if I get 4 packets and their amount is somewhere between here, then I have a good cup of coffee. This is the good cup of coffee threshold. If it's too far down below, it's not sweet enough. If it's too far above 9, it's too sweet. Right in between 8.5 and 9 is what I want. So we're going to do 2 z-score calculations. We'll do the z-score calculation for 8.52. So it's from the mean divided by the new standard deviation, which is right here. And we get a z-score for 8.52, z-score look. So a z-score measures the position. So the z-score for 8.52 should be negative because it's below the mean, and a little bit less than 1, I guess. So a little bit, beyond -1. So it's negative 1.13 after this calculation, which seems reasonable. We'll do the other z-score calculation for 9. You could do it, which would be really nice. I don't even have to do this in my calculator. I can clearly see on my distribution that it must be 2. It's 1, 2. A z-score is number of standard deviations away from the mean. If we are finding this probability, really, this probability is the same as finding the probability between these two. If we look up These two, if we want to find this area here, we'll do the larger. So when we look this up in our z-score table, if I look up 2 in our z-table, it's 9.977. So we take the larger minus the smaller, negative 1.13. So 0.1292. And so we get a probability of 0.84. There's about an 85% chance that Mr. French's coffee will taste right. Here's another example of SAT scores. A college uses SAT scores as one criterion for admission. Experience has shown that the distribution of SAT scores among its entire population of applicants is such that we have SAT math score, we'll call X, has a mean of 519 and a standard deviation of 115. So the average math score is 519 on the SAT for this college, and typically a student will deviate from that mean by about 115 points. And we're going to call that random variable X. We'll call the SAT reading score, we'll call that Y. And the mean of Y, the mean reading score is 507. The expected value is 507. And the typical deviation from that expected value is 111. So the question is, what are the mean of the standard deviation of the total score? So if we were to add everybody's mean and reading score, what would that distribution look like? Well, I know that the mean of X plus Y would be if I expect 519 on a math score for a student and 507 for a reading score for that student, then I would expect 1,026 for their total score if I add those two together. But how much deviation should I expect to see? What would the standard deviation be of X plus Y? Remember that we cannot add standard deviations. We cannot do this. We can't just add 115 plus 111. That's not how the standard deviations work. We can, however, add variances, but it would not be appropriate in this case. The variance and standard deviation of the total cannot be computed from the information given. SAT math and critical reading scores are not independent because students who score high on one exam tend to score high on the other exam. This would be an unsafe assumption to make. Yeah, so students that are going to perform like really high on their math score are also students that tend to score really high on their reading score. Think about that. So we can't, like, making the assumption that they're totally independent from each other is not true. So if your reading score is like through the roof, your math score is probably going to be pretty good as well. Yeah, sure, there's people that score super high on math and super low on reading, but if you have a super high math score, your reading score is probably not going to be too bad. And vice versa. If you get a super high reading score, I would be confident to say that your math score is probably pretty good. And I know that there's obviously outliers there, but the idea that students that perform well on one will perhaps perform well on the other one is something to consider. So in this case here, we cannot just simply assume independence. So since with the information given, we don't know if they're independent, we cannot calculate the variance. The reason why we can't do that is because a while ago, when we actually showed where the variance comes from, when you multiply those probabilities, each of those probabilities were not affected by knowing one outcome, and we could just simply multiply them together. That's not the case now. So we can't just simply multiply the probabilities in all those different possible combinations. And so that makes it so we can't find our standard deviation or add the variances. Let's take a look at an example that might utilize differences between random variables. The diameter, C, of a randomly selected large drink cup at a fast food restaurant follows a normal distribution with a mean of, so I'll just do this. We have C. C is equal to diameter of large drink cup, a randomly selected large drink cup. We know it's normally distributed with a mean, so I'll say mu of C is 3.96 inches and a standard deviation of 0.01 inches. So on average, the diameter of, machines make these cups and lids. So on average, the lid will have a diameter of about 4 inches, and typically it'll be off by a very, very small amount because machines are making these things. So I'm not surprised that standard deviation is so low. And then let's say that the diameter L of a randomly selected large lid falls in almost, okay, so we'll have another random variable L. We'll say L is the diameter of large lid. It's randomly selected. So this is the lid that like goes on top of it. And we're going to say that the mean of the lids is 3.98, and the standard deviation of the lids is 0.02. For a lid to fit on a cup, the value of L has to be bigger than the value of C, but not by more than 0.06 inches. So what is the probability that a randomly selected large lid will fit on a randomly chosen large drink cup? So we want to make sure that the difference of these two random variables isn't too big or too small so that they match on each other. We want to make sure that the difference between these two is like close to 0, probably a little bit above 0. So we're going to define the random variable D as L minus C to represent the difference between the lid's diameter and the cup's diameter. The random variable D is the difference of two independent normal random variables, so D is going to follow normal distribution as well. So we'll say the lid minus the cup. So the lids, we hope that the lid is a little bit bigger than the cup, so it kind of fits over it. The lid to be a little bit larger, and I kind of want this to be positive, just to make our calculations easier. So let's take a look at the distribution of how this would occur. So the differences between these, so the difference between these is really just subtracting the two means. So it's 3.98 minus 3.96. So the mean of the difference is 0.02, which is good. That's good news. So this means that on average, we expect that the difference between the lid and the cup to be a little bit more than 0, which is perfect for lids and cups. Okay? And so now we're going to do the standard deviation of the differences. But we'll start with the variance. Remember, we never add standard deviations when we combine random variables. This is going to be the variance of the lid. Now here's the surprise. This is an idea that we talked about on the slideshow. You actually always add variances. Whenever you introduce more variables, whenever you combine or take away, you're only introducing more variability. So we are going to add the variances always. You always add the variances if you have independent random variables. So we are going to take, looks like 0.02 squared plus 0.01 squared, and we get a variance of 0.0005. And if we square root this, we will get our standard deviation, which is 0.0224. All right, so let's go back to the question at hand. For a lid to fit on a cup, the value of L has to be bigger than the value of C, but not more than 0.06 inches. L needs to be larger than C, but not more than 0.06 inches. In order for a lid to fit on a cup, L needs to be larger than C. The difference needs to be larger than 0.06 inches. Let's go ahead and just draw our normal curve. Okay, so this is the distribution of the differences. So recall that we want the difference to be positive because that would mean this is the differences, so L minus C. We want the difference to be positive because that means that L is larger than C. The lid is larger than the cup. So that needs to be happening. So let's go ahead and find where 0 is. 0 would be located maybe around here. This is where 0 is located. So I want the difference to be larger than 0. However, if it's above 0.06 inches, then the lid is going to be too big. So 0.06 is like right here-ish. This is a little bit more than 0.06. So here's 0.06. So this is the sweet spot. This is the place where the lid is larger than the cup. So a difference of 0, so it's going to be above that, but below 0.6 if it's too large. So we need to find this probability here. We're trying to find the probability that I'll say D, because we defined the difference as L minus C, is between 0 and 0.06. Oh, also, why are we able to add the variances? Well, in this case here, we know that the machines are producing these lids and cups, so it's safe to assume, especially with machines, it's safe to assume that we do have, like, the lid machine has nothing to do with the cup machine. You know, that's a pretty safe assumption. So we're good to go. We can add the variances because we have independence. So we will do the calculations here. So we'll find the z-scores for each of them. So 0 z-score is negative 0.89. The z-score for 0.06. Remember, z-scores measure a position. Negative 0.89 kind of makes sense because 0 is a little bit less than 0.02. 1.79. So if we're finding the areas, there we go. If we're finding the area between these two positions, we look each of these up in the z-score table, we'll find those percentages. We're going to subtract the larger percentage from the smaller. The larger percentage, so the z-score for 1.74 is 0.9633. So 96% of the curve, including this tail. So 96% is below this, but we have to subtract this tail here. So 0.1867. So the difference between these two percentages is 0.7766. There is about a 78% chance that a randomly selected lid will fit on a randomly selected large drink cup at this fast food restaurant. Roughly 22% of the time, the lid won't fit. I don't know about you. So we have a probability of about 77%-ish, about 78%. So about 78% of the time, a randomly selected lid will fit on a randomly selected large drink cup at this particular restaurant chain. I don't know about you, but that means like 22% of the time it's not going to fit, which is a little bit more than 1 in 5, which is kind of not good. So if we had to make a decision here, I'd say that this is kind of not a good, I would probably say this is not a good setup. Fix your machines or buy a new one. So that concludes combining random variables. There's a lot of ideas in here that are crucial. Some big ideas is that you can add variances. You only add variances. You cannot add standard deviations, but you can only add variances if you know, or if you can safely assume that the random variables are independent random variables, meaning that one of them will not affect the other. So in this case here, we had two separate machines. So if one machine broke down, that doesn't change the other machines being able to break down. You only add variances. Be mindful of your z-score calculations. Yeah. So the suggested practice for this lesson, oh, I can just edit this in post and put the suggested practice. Yeah, okay. Is 47, 49, 51, 53, 55, 57 to 59, and 61. So I recommend that you do those problems. If you have questions on them, please let me know. You can post questions in the comments. If there's a lot of questions, I might just make a video going over some suggested practice problems. That'd be great. We're going to get into a huge section in 6.3. A lot of important ideas coming at you here in a little bit. So stay tuned. We have 3 more lessons for this unit, and then we have all the content that we need. So in about 3 more videos, in 3 videos, we are going to be starting our review. And it's strictly going to be free response. So all your interpretations, know them. If you struggle with multiple choice this year, fun fact, you won't have multiple choice, which is a blessing and a curse. It's still great problems. Khan Academy is really good practice, but I certainly suggest that you practice your interpretations and explaining your thinking. Do suggested practice problems. Those are great free response questions. Thanks for the folks that are doing it. Thanks for the folks that are asking questions. This has been fun. This has been Mathing. Tell him to sit. Now back away.